Alright, I've got a bunch of stacks here. And then this is obviously going to go on top of the tallest one, so let's just go ahead and take those out. They've got a 1, 2, 3 that we start with.
Okay.
And that goes, let's pick one there, go in one more, and go up one. It kind of, I mean, obviously it's the same no matter where you start. You just don't want to run out of room off the board. All right, I need a twofer to reload that. All right, now this is an interesting one to track because it needs to go boom, boom, and then down. It's almost like playing chess. Has anyone ever built hexagonal chess? That would be really interesting.
Okay, this one's like this.
Yeah, I think you're right. Because if I go down, let me check it another way. If I go down here, got 1, 2. Nope, I'm already off 2, 3. I think it needs to go over one more. We can probably find out when we start putting stuff on. Oh, it's got the magnetic cannon. Finally, magnetic cannon. Okay, we're gonna need a long track, a super long track. I forgot there were longer tracks than that. And then 2 small tracks. So very few tracks on this one. 6 of the turns. The release, obviously. Oh, the release does not go to the highest. Oh, the magnetic cannon is going to shoot it up higher. Oh, ho, ho. How does that give it more energy? I don't know. We'll find out. So the magnetic cannon is going to go on this one. Or not the magnetic cannon. The launcher is going to go on that one. And then I need the magnetic cannon. And obviously we need our catcher. Should I put it down somewhere? Oh, it's over here. Okay. And so,
Here.
yeah, because that needs to connect just with a 1 hex over this way. Okay, there's more guideposts here. So, okay, so it's interesting. They always have you start with these, even if some of the white ones are going to go directly onto the grid. I feel like having the layer by layer might be, I don't know, maybe this is the way my brain's working today. Alright, so we need to go this way. That's good. And then we get the very long track. Yes, yes. Okay, this is where we were off by a single hex, so since we already got those set up, let me get that one over there. And so everybody here needs to move southwest by 1 hex. We'll get a broad curve there. This over here.
Tiny curve.
Perfect. And then one more here.
Tiny curve.
Tiny curve. This goes here. Okay. All right, now we get to learn how the magnetic cannon works. So I'm going to need extra marble here. And somehow that's supposed, so from a physics perspective, this is interesting because the rule of roller coasters is you can't go higher than you start, right? Unless you're riding the Hulk at Universal, because then it launches you and you can go higher than you start because you start out with kinetic energy in addition to potential energy. So this is interesting to me because this guy starts out 1, 2 blocks high, and he's supposed to get 1, 2, 3 blocks high, which I thought was impossible. So somehow this magnetic cannon is going to give the thing energy. I guess we'll find out. First, let's check. Have we reproduced this appropriately?
Looks like it.
I think so. All right. Would you like to do the honors on the first magnetic cannon?
And I'll give the super scientific countdown. 3, 2, 1.
makes up for all the times I mapped.
Whoa!
How does that work?
Whoa!
How on earth is... Okay, first of all, I need to actually connect this thing here. Sorry for the anticlimactic
I was not
ending.
expecting
I was not expecting that.
that.
Okay, now getting this thing reattached is an interesting problem because I have to pry it out of the magnetic can because it doesn't go through to the other side. Oh, goodness. So how does having two of those... What happens if you launch it with one on this side? Absolutely nothing, okay. Oh, I think I know what it does. I think I know what it does. Alright, so... Oh, no, there's be two on the other side. Okay. Let's go again. I messed up your run there. You get to launch it again.
Alright. 3, 2, 1. That's so cool.
Okay. So where is the extra energy coming from then? Because it starts out here at rest.
Mm-hmm.
We have 2 blocks worth of potential energy and no kinetic energy. We come down here. Actually, I'm not measuring that correctly, am I? Because I need to include the white ones. If I include the white ones here, I start out with 1, 2, 3 blocks of potential energy. But then by the time I get up here, I've got 1, 2, 3, 4 blocks of potential energy. The only thing I can think of is that when it strikes here, no, these are flat. These don't have an incline. I was trying to think it's coming in higher. No, that doesn't work because then it would keep that potential energy. How does it end up launching? It's got to have something to do with the fact that there's 2 marbles on this side, right? So somehow this thing is changing the amount of kinetic energy on this side, or changing the amount of momentum. All right, this is
So when this is against the magnet and this one strikes it, since there's a marble in front of it, when energy works, if something hits something and that one doesn't move but the other one moves, does it like double that energy?
Well, so we have this rule called conservation of energy, where the total amount of energy in the universe has to be constant. Now you can also apply that to a local system. So if you could isolate several objects together, the total amount of energy in that system has to remain conserved. It can change forms. So like right now, I'm making my system the... Oops, I somehow ended up with a 4th marble. That's not a closed system. If I make my system the 3 marbles and the Earth, then my total energy between potential and kinetic needs to be conserved. So right now it's all kinetic energy, it's all potential energy. Nobody's moving it stored in that height. Just before it hits here, I've gotten rid of all my potential energy, I've converted it all to kinetic energy. But then we have a collision, and collisions are interesting because you have to conserve kinetic energy and you have to conserve momentum. And you don't always conserve kinetic energy, but it's not going to make more, right? Because you can lose it to sound. There's the sound of the thing hitting, there's heat loss, there's vibration, etc. Oh, I know what it is. Where's the energy? Okay, this is a magnet, right? And the magnet is attracting it.
Okay.
And so that is exerting a force that then accelerates this thing forward. Now there's a problem with that still, in that where is the energy coming from for the magnet? Is it so when 2 permanent magnets accelerate toward each other, oh, there's still electric potential energy there. Okay, so I have not included in the system. So magnets, let's talk about magnets now.
Yes.
Magnets are interesting in that, you and I have an intuitive understanding of magnets. If you grew up with a refrigerator and you put magnets on, you have an idea that magnets will make things stick. There's a problem with that in terms of the physics, though, because the magnetic force itself never does any work. It can never change the energy of a system. And so anytime you have something accelerating like that toward a magnet, it's actually an induced electric force that's accelerating it. Griffiths makes a very big point of this in his electromagnetic theory textbook. But the magnetic field cannot do any work, so it's got to be an induced electric field. And so as this thing gets closer, there is also electric potential energy that we have to consider. Now, the reason you need an extra one here, right, is because if I take this one out, I'm just going to flip it around next time I need to do that. The reason you need an extra one is because if you have the same mass coming in, like you were saying, the energy is just going to transfer, right? Because if I do this, it's not going to go anywhere because there's a symmetry on either side, and so the magnetic force is working just as well here as it is over here. On the other hand, if I put another one here, right, magnetic force and electric force, they decrease with distance. They're going to get weaker. And so this is actually increasing the distance. So this thing doesn't get quite as strong force there, and we are winning out by the force of the collision. Excuse me, other way around. There has to be two on that side. Just look at the diagram. And so, yeah, excuse me. So it's actually, okay, right. So this one is getting this much force. It's getting, you know, a force that's inversely proportional to this, whereas this one is not held on as tightly. It's in place because it's at rest, but it's not being held in place with as strong an electric force. And so when this guy comes in, that one can shoot out faster because it's got lower electric force. Okay. Future Brian, let's make a video that actually explains that and maybe even models it, because that's freaking cool.
It is really cool.
Oh man, okay.
I love that.
So,
it's even more exciting knowing what's going on.
Yeah, I mean, because you look at it like, oh wow, it launches it, but then you think about it, you're like, no, wait a minute. I can't, because here's the thing, if it were just a matter of it going through, it would be able to go up by itself, but because it is actually important that it's a magnet there. So you could test it by fashioning a piece similar to that, but just put in a block of plastic, and then it's not going to come out like that, right? Because I've been comparing this to the Newton's cradle demo, right, where you lift up one sphere, another sphere comes out, one goes in, one comes out, because that's the way the conservation of momentum and conservation of kinetic energy have to work out. But with this, there's a magnet in the middle. And so another neat way you could do this would be you could do Newton's cradle but put a magnet.
Oh, that would be fun.
That would be a really fun thing to build.
This one's cool.
That was really cool. We have learned how the magnetic Canon works.
That's awesome.
All right.
This is my favorite so far.
This is definitely the favorite so far, yes.